Hello everyone to the third lecture of this course. In this lecture, we will be learning about the proposed NOMA with dual transmission in single cell network. So the proposed system of a single cell network that is employing dual transmission is presented in the figure. In in this uh, in this system, we consider a scenario where we are considering a wireless system in which we have one transmitter and two receivers. So it is a multi user communication system, and those under the risk of eavesdropping. So our goal is to design a system that is robust against security issues, and in the meanwhile we ensure that the signals we transmit are totally secured even by the internal network. um by internal network I mean that the receiver of that user 1 and user 2 receiver, they are not able to hear each other's information, and even if they listen, they do not they are not able to decode each other's signals, and both receivers receive and decode their own signals only. And in this system their communication is undergoing under the in the presence of an eavesdropper, which we consider as a passive eavesdropper. So, firstly, the data vector or the data sequence of user 1 is represented by x1, and data vector or data sequence of user 2 is represented by x2. These are the bits and the streams, and each one goes through a modulator. It can be BPS. It is, we suppose that it is a BPSK modulation, and the data is first serial, so we make it like parallel, so it becomes a vector, like a column vector basically, if you see on a MATLAB simul coding. So my most interesting contribution here is in the so most interesting contribution here is in the devising and inventing the precoder matrices that can achieve all the goals that I have talked about. The goals can be such as to make it secure, to avoid interference between the users, to avoid successive interference at users, because we want to shift all the complexity to the base station so that it can be used in low computational IoT devices, and there is no complexity at the receiver side, unlike the conventional power domain NOMA discussed in the previous lecture. So we are superimposing these precoders with the data. The data is superimposed with the precoder, and why we call it non-orthogonal? Because we are intentionally introducing an interference by putting x1 and x2 data streams on top of each other, and we design the precoders intelligently in such a way that when our signal passes through the channel, they get separated at the receiver, and we receive it successfully at the receiver like whatsoever. And really the intelligence in is in the design of precoder. So how we are, by doing this, we are like introducing a new kind of freedom and having another transmit antenna, which transmits the signal in the signal is transmitted here basically in dual transmission. First, here there are two antennas. The first round of the transmission occurs from the first active antenna, and the transmit data is transmitted to all the users. And the second round, the second antenna is activated with the help of switch, and second antenna transmit the signal. So there is a two round transmission. from the two antennas. So the it this process of transmitting the information is called can of using multiple antennas for transmitting the data is called antenna diversity, which is transmitting the same data from two different antennas. On the other hand, you can also think of it as a non-diversity technique because the precoders used in as a because we can consider it as antenna diversity basically because we are using because yeah we can also call it non-antenna diversity because we are using separate set of precoders for each transmission of data from each antenna, separate precoder matrices for separate antenna. So it can also be considered a non-antenna diversity technique because the transmitted data from antenna 1 is totally different than that of the transmitted data from antenna 2 in terms of precoders. The data is same, but the precoder matrices are different, and that makes it different. So the novelty behind this the proposed NOMA scheme is that it requires no successive interference cancellation. There is dual transmission from two active antennas. Sorry, I did a mistake here. It is like dual transmission. It is not simultaneous transmission. It is dual transmission from two active antennas, and it provides perfect security against both internal and external eavesdropping. It is less complex and suitable for IoT devices like 5G and beyond. Uh, the proposed NOMA versus the conventional NOMA. Here is a depiction of the proposed NOMA with the conventional NOMA. You can see that the proposed NOMA transmits the data in dual transmission and it is combined at the receiver, whereas in the conventional NOMA, um, there is successive interference cancellation and power sharing, which degrades the signal. Whereas we don't require successive interference cancellation because there is automatic interference cancellation when we transmit data in two rounds. That gives an edge over the conventional NOMA. So the goals coming towards the proposed algorithm. In the proposed algorithm, we discussed the we achieved the goals, several goals, that is security against internal eavesdropping, security against external eavesdropping, security for low processing devices. Now discussing the algorithm here, M1A, M2A are the precoder matrices, X1A, X1 and X2 are the transmitted data bits or streams. M1B and M2B are again the precoder matrices, and X1 and X2 are the transmitted data bits. Here, H is the channel, and A represents the user and antenna. So the Y11 here represents the transmitted data from first antenna at user 1, transmitted data from first antenna at user 2, and the transmitted data from first antenna to the eavesdropper. Whereas Y12 represents the transmitted data from antenna 2 at the first user and the transmitted data from antenna 2 to the second user and the transmitted data from the antenna 2 to the eavesdropper. So H here is the channel, and as we told in the previous slide that the transmitted data bit is superimposed with the precoder matrices. So in the first round, when antenna 1 is transmitting the M1A precoder is superimposed and multiplied with the data bits X1 of the first user, and M2A similarly is multiplied with the superimposed with the X2 second second user data bits, and then here H represents the channel between the first user and the first antenna. So similarly, same process goes for Y21, Y31, and for Y12, Y22, and Y32. And in this way, the data is transmitted securely. So the received signal at user 1 is the combination of data from both the antennas in both the rounds, first round and the second round, from antenna 1 and antenna 2. And it is the combined received signal from both the antennas. So we add both the signals, and it should be noted that we have not added here the noise terms, because it does not affect our system model, the noise terms. So the first term in Y1 is the desired term. Similarly, the combined received signal at user 2 can be written as follows. For user 2, the second term is desired term, while the first term is not desired for it, and it is considered as the interference. For eavesdropper, both the terms are desired for it. For the design of precoder matrices, the intelligent precoder matrices M1A, M1B, M2A, and M2B, we consider the desired term of user 1 as the identity matrix, and the desired term of and the non-desired term, that is the interference term of received signal at user 2, as as 0. Similarly, for designing the other sets of precoder matrices, we consider the desired term of user 2 as equals to 1, and the non-desired term, that is the interference term of user 1, as 0. And when we simultaneously solve these both equations for M1A and M1B, we will get the values of M1A and M1B. And similarly, when we will simultaneously solve it for M2 and M2B, we will get the values for M2 and M2B. That is, precoders will be superimposed with the data streams. And here goes the values of the intelligent precoder matrices. So with this, we ends up with the algorithm and the mathematical equations and the mathematical model that is behind this proposed secure single cell communication system with NOMA based transmission. So this explains the our mathematical model for single cell communication system. In the next lecture, we will be discussing about the simulation codes behind this algorithm for the simulation. I hope you find it useful, and you will follow up with the lecture in the next upcoming lecture. Thanks for joining.